But what I want to talk about more than anything right now is the space between the stars. When we look up on a good night, we see a star there, don't we? We see them scattered across the sky. And we might be forgiven for thinking that between the stars is just empty space. But the question is it empty space? And I can tell you now it's not. But in order to get a handle on how empty or not empty it is, we've got a little experiment we're doing. Now, you've all got, hopefully, one of the little plastic cubes that you were given when you came in.
I've lost mine, sorry.
All right, well, I'm sure we can get you one. Now, these cubes are actually a centimetre on a side, so they are a cubic centimetre. And this room we're in, it's obviously full of air that we're breathing. Now, I think many of us know that air is made primarily of oxygen and nitrogen, molecules of air. Now, I'd like you to sort of give us your guesses. How many molecules of air do you think there are in 1 cubic centimetre of air? Like the air in this room.
Isn't that hydrogen?
Yeah, we're coming to that. So how many molecules in a cubic centimetre? Any guesses, please? Don't be shy.
Well, it was a million.
A million. We've got a million?
100 million.
100 million?
10 million.
Billion.
A billion? Well, you're going in the right direction. You're going in the right direction. It is a great many. In actual fact, it's 10 million in 1 cubic centimetre of air. So there's two things there. There's an awful lot of them, isn't it? It's a very big number. It means that molecules are very, very small then, doesn't it, if you get that many in a cubic centimetre? Well, 10 million is a quite a clumsy number, 1 followed by 19 zeros. So scientists have a shortcut for this. We say 10 to the 19, or 10 multiplied by itself 19 times. And that's how we deal with these really big numbers. It's much easier to say this. So 10 to the 19, that's 10 million. Okay, so that's the air in this room. And we actually say the number density, n, is equal to 10 to the 19 per cubic centimetre. Right. Now, I want you to imagine that you've come to Manchester University, to the laboratories there. A lot of experiments are done in a vacuum. So they have these big vacuum chambers with pumps on them to pump all the air out of the chamber. Now I can tell you they can't get all the air out. Some of it gets left behind. It's impossible to get it all out. So any idea how many atoms or molecules are left behind, even per cubic centimetre, even after we've been pumping away for days? Any guesses? It's obviously a much smaller number than 10 to the 19. 100? A million? Okay, well, it's actually 10 million, 10 to the 7. So a vacuum, which would make you suffocate if you were put in it, what we call a vacuum, still has that many molecules in each cubic centimetre. So air in this room, 10 to the 19. What we call a good vacuum is still 10 to the 7, or 10 million. So the question is, the space between the stars, what we call the interstellar medium, ISM, how many atoms do you think there are in each cubic centimetre of space between the stars?
10 to the 27.
127, a very precise number there, very good. Any other?
10 to the 27. No.
10 to the 3.
10 to the 3, 1,000. Okay, well they're all good guesses. Actually, on average, there is 1 atom per cubic centimetre in the interstellar medium. So it's not empty. But that is very, very tenuous, isn't it? Very, very thin. It's much less than what we call a good vacuum. But the thing is, and here's a summary of these different numbers, from the core of the sun, the air in this room, all the way down to the interstellar medium. Although that doesn't sound a lot, new stars come from the interstellar medium. All those single atoms per cubic centimetre add up. And in actual fact, if we think of our galaxy as a whole, if we take all the stars and the planets and the comets and the asteroids, they only take about half of the ordinary matter that's in our galaxy. The roughly other half is all that dust and gas that's in the space between the stars. Because
That's dark matter.
so the distance between the stars, because it's such a big distance, huge distance, there's, even though the amount of matter is very thin or tenuous, it adds up to a great deal. Now, as somebody said, a big part of it is hydrogen. About 3/4 of the interstellar medium is hydrogen. More or less the rest of it is helium, and then there's tiny amounts of the things we're more familiar with, oxygen, carbon and nitrogen. And also there's dust in the interstellar medium, which I mentioned earlier. Very tiny particles of dust, either based on carbon or based on silicon. And in actual fact, we said that on average it's 1 particle per cubic centimetre, but in reality there are different types of region in the interstellar medium. Some of it is very hot, temperatures are very high, the densities are even lower. But there are other places like molecular clouds, which is what we're interested in tonight, where they're very cold, but the density's still higher than 1 per cubic centimetre. Now I just need to mention that we measure temperatures in astronomy in degrees Kelvin. And degrees Kelvin are the same size as degrees centigrade, it's just that they start at a different place. And the coldest temperature you can get is absolute zero. I'm sure some of you know, many of you know this, minus 273 degrees centigrade. So degrees Kelvin start at this temperature, so we call that 0 Kelvin. So when we say 30 Kelvin for a molecular cloud, we're actually meaning minus 243 degrees centigrade. So extremely cold, extremely cold. So we mentioned dust. Now the dust in the interstellar medium, it shows its existence by its effects. For instance, starlight, over here, far away from this image, up here there are some stars, and their light is reflecting off this dusty region in the interstellar medium. So we can see the dust when it reflects light. We can also see, we can also,
Shut up. Oh, sorry, changes are very other.
we can also see shells of dust. What's happening here, there's a star in the centre of this image. We can't actually see it. This is about 4 light years across this region. It's very, very big. And this star here is at the end of its life, and it's shed its outer atmosphere, and that's moved away and eventually formed a shell of gas and dust. And then the star itself has sort of flashed and sent out a pulse of light, and 2 years later it's lit up this huge circle of dust that surrounds this old star. So we can see the dust in the interstellar medium in situations like this. All these other stars, they're all foreground stars. They're sort of in between us and this actual object. The other way that we see the dust, and we saw it in the earlier images, is when there's so much of it, it actually blocks the star light, the actual images of the stars that we can see all around here in the background. It actually blocks the light coming through. And I'll just point out here, there is a region of young blue stars, and we're going to talk about those in a minute.